Derivative of elliptic integrals of first and second kind. Yeah. So here are the derivatives, but we are going to prove this. And first of all, let's define the elliptic integrals. Elliptic integral or E. This is actually the second elliptic integral. Yeah. And this is defined as integral from 0 to pi by 2 of square root of 1 minus k square sine square theta d theta. Yeah. And the complete elliptic integral of first kind, k, is defined as this k is the input variable and this k is the function. Okay. Integral from 0 to pi by 2 of 1 by square root of 1 minus k square sine square theta d theta. These two are the definitions, and I'm just sharing it for the sake of convenience and formality. Now let's begin. So let's differentiate the elliptic integral of second kind, e of k. We know that this is actually the integral. This is actually the integral from 0 to pi by 2 of square root of 1 minus k square sine square theta d theta. Yeah. Now since the integral is in the world of theta, this is just the partial derivative with respect to k, so we can take it inside and make a partial derivative with respect to k. So sine theta will be constant in that case, and if we differentiate, we have 1 by 2 root 1 minus k square sine square theta, and then minus sine theta is constant in front of k square. The derivative of k square is 2k. Yeah, this is the case, and then we have d theta. Yeah, and now what do we do? So now we basically cancel the 2's and take 1 by k common, so that we can replicate the minus k square sine theta plus 1. We will try to replicate this and now subtract 1. Yeah, and there's a reason for this, because there will be a cancellation from denominator if we do that. Yeah, you might probably notice that now there's a cancellation, and that simplifies the work. 0 to pi by 2. Now this is square root of 1 minus k square sine square theta. Yeah, and plus, sorry, not plus, minus 1 by root under 1 minus k square sine square theta. Yeah, and d theta. So now we know that the first integral is just the elliptic integral of second kind, e of k. The second one is elliptic integral of first kind, that is k of k, capital K of small k. Yeah, and this is the answer for the first one. Let's see if this is correct or not. Yeah, 1 by k capital E of k minus small e of k. And it's so like interesting that the derivative of elliptic functions is again in terms of elliptic functions. So that's really a nice property. Like just like the derivative of just like the derivative of e was again e. Yeah. So similarly here also the derivative of some functions is again in terms of the same functions, and that's really nice. This is also nice, but somehow here is messed up. But yeah, let's try to prove this as well. Derivative of k of k, or derivative of k of k. So now we know that this is the derivative of integral from 0 to pi by 2 of 1 by root under 1 minus sine square theta k square d theta. Yeah, again we take it inside and do the partial derivative, 0 to pi by 2. Since this is 1 minus sine square theta k square to the power minus 1 by 2, so this will be minus 1 by 2, 1 minus sine square theta k square to the power minus 3 by 2. Yeah, and then if we differentiate this, we have minus sine square theta times 2k. Yeah, and then d theta, and 2 cancels out, minus minus cancels out, and so this will be integral from 0 to pi by 2 of k sine square theta, and then by 1 minus k square sine square theta to the power 3 by 2 d theta. Yeah. Now if we take 1 by k common, we can make it k square sine square theta. Also if we make it as minus 1, then we will minus 1, and do the plus 1 minus 1 to replicate this function. Yeah. So we have minus 1 by k, and now this is integral from 0 to pi by 2. Now this is 1 by root under 1 minus k square sine square theta. Yeah, and this one is minus 1. Basically let me write it plus 1 by k, plus 1 by k, minus minus plus, integral from 0 to pi by 2 of 1 by 1 minus k square sine square theta to the power 3 by 2, and then d theta. Yeah. Now if we take just 1 by 2 common, now this is minus of capital K of k. Yeah? And it remains to find this thing out. For this one, we will try to use the hypergeometric function and then use some transformations. Yeah, that way it will work. Okay, fine. Now if we make a substitution that x equals sine theta, this will go from 0 to 1, and then 1 minus 1 by 1 minus k square x square to the power 3 by 2, and then 1 by root under 1 minus x square dx. Yeah, and after that also make substitution that y equals to x square. If we make that substitution, y equals to x square, we get integral from 0 to 1, 1 by 1 minus k square y to the power 3 by 2, and then over here this is 1 minus y to the power minus 1 by 2. Yeah, and now next, since we have made y equals to x square substitution, we will have 1 by 2 y to the power minus 1 by 2 dy. Yeah. Now next is 1 by k, and this is minus k of k, plus, now this is 1 by 2, we can take outside, integral from 0 to 1 of y to the power 1 by 2 minus 1, 1 minus y to the power 1 by 2 minus 1 by, this is 1 minus y times k square or to the power 3 by 2 dy. Okay, now this is in terms of the integral of hypergeometric function. Yeah, you might recall that. So basically we know that the hypergeometric function integral is integral from 0 to 1 of y to the power b minus 1 or 1 minus y to the power c minus b minus 1 by 1 plus dy to the power a, and then dy. If we have this integral, this actually equals to beta of c minus b comma b, and then hypergeometric function of a comma b comma c comma t. Yeah, so we'll use this. That gives us 1 by k, this is minus k of k, plus 1 by 2, that gives us beta. C minus b is 1 by 2. Yeah, 1 by 2, b is also 1 by 2, 1 by 2, then 2 as 1, A is 3 by 2, or B is 1 by 2. Now C is the sum of these two expressions, yeah, C minus B and B. So 1 by 2 and 1 by 2, that's 1. And we have T as K square. Yeah. Now after this, we will try to use the gamma function for this one. Yeah, that gives us 1 by K, or minus K of K plus 1 by 2. We know that this is gamma 1 by 2, gamma 1 by 2 by gamma 1, and that is root pi times root pi, so that's pi. Now over here in this one, we will try to use the Euler's transformation. Yeah, Euler's transformation. We know that 2s1 of a b c x, this is actually equal to 1 minus x to the power c minus b minus a, and then times, or 2s1 c minus a c minus b c x. This is the Euler's transformation. If we use that over here, we get 1 minus k square to the power 1 minus 1 by 2 minus 3 by 2. That's 1 minus 2. So minus 1, and then 2h1. See, 1 minus 3 by 2 is minus 1 by 2. 1 minus 1 by 2 is 1 by 2. 1, 1, and then k square. Now you notice something. This is actually the definition of what? E of x, isn't it? E is E of k. In my previous video, I've already found the hypergeometric series for E of k, k of k. Yeah. So this is the hypergeometric series for E of k. So that's how we got an expression in terms of the known thing. Yeah. So 1 by k. This is minus k of k plus, we have 1 by 1 minus k square. Sorry, this along with the pi by 2 is that E of k. So pi by 2, or 2s1 minus 1 by 2, 1 by 2, 1 k square. And this is the E of k. That's why we have 1 by k. This is E of k by 1 minus k square minus k of k, and this is the answer. Let's check. 1 by k, E of k by 1 minus k of k. Yeah, that was the answer. To talk about the flow, we first differentiated. Yeah, and this was simple. This was just k minus k of k. Over here we transform to hypersymmetric series first. Yeah, and then use the Euler's transformation, and this was a familiar one, so that it was actually an kind of accident. Yeah, just surprisingly we got that. Yeah, accidents do happen just like this one. And hypersymmetric series was not really invented. Maybe it was just for fun or just to generalize, but yeah, it does have some nice applications over here. So sometimes maths that is made for fun might be useful later in the centuries. Yeah, this is one of the example. So yeah, hope you enjoyed the video. Thanks for watching. I look forward to seeing you in the upcoming videos too.